Well, this is your introduction to balancing. In balancing, we're going to work with some complex chemical equations. The principle is that we want the same number of elements on both sides. That's because we can't destroy matter when we do a reaction. So there has to be the same number of starting pieces on the left-hand side of the equation, the reactant side, as there are on the product side. There simply has to be just as many atoms on both sides of the equation. That's just the way it is. They never disappear. They cannot be destroyed. So what we do first is work with the most complex polyatomic ion, and we're going to treat it like a unit. What I mean is PO4, that's a polyatomic ion, and we're going to work with it by just treating it as a whole. So on the left-hand side, you can see there's just one of those, and on the right-hand side, there are two. So that's the first problem that we're going to attempt to solve. So that means just to start off with, what we're going to do is put a 2 right here. That's the first step. Why? Because now on the left-hand side, there are 2 PO4s, and on the right-hand side, there are 2 PO4s, and we're good there. So now we're going to attack the magnesium problem. See, on the right-hand side, there's 3 magnesiums, and on this side, there is just 1 magnesium. So we're going to solve that problem very simply by putting a 3 right here. So now we've got 3 magnesiums on the left, and we've got 3 magnesiums on the right, and we're almost home. So now, rather than adjusting this, we're good. We've got the right number of phosphates, and we've got the right number of magnesiums. All we have left to do is adjust the waters. That's it, H2O. So we're going to do it this way. We're going to deal with the hydrogen first. Let's deal with the hydrogen first. Okay, so on the left-hand side, how many hydrogens are there? There's 2 times 3 right here. In phosphate, that 2 is multiplied by the H. There are 3 H's in phosphoric acid. And so if you have 2 of them, then you have 6 hydrogens. So on the left-hand side, there's actually 6 hydrogens here. And in addition to that, there's actually another 6 right here. See, this 2 multiplies by that 3. There are 2 hydrogens in these 2 hydroxide ions right there. And those 2 hydrogens will be multiplied by 3. There'll be 3 of these and 2 hydrogens in each. So that means that there's actually 6 hydrogens total there. So how many hydrogens do we have on the left-hand side? Actually, it turns out we have 12 total hydrogens on the left. So what number do we need to put here? Easy. We're just going to put 6, because that 6 multiplied by the 2 in water for H2O, right? That gives us 12 hydrogens on the right, and we're finished. We've got the right number of elements. If you want to prove that we've got it, we can actually just take a look at the oxygens to be sure that we've got that right. On the left-hand side, look at how many oxygens there are. There's 2 times 4, and so that would be 8, plus an additional 3 right there, right? So 8, an additional, 6. So there's 8 and 6 is 14. So there are 14 oxygens on the left-hand side. And on the right, if you take a quick look, you've got 6 times just 1, because there's only 1 oxygen and hydrogen. That's 6 there. And in addition to that, there's another 8 here. 2 times 4 is 8. So there's actually 14 oxygens on the right as well. So you've got your first solution to a very complicated balancing problem here. And again, the principle is work with the most complex element first, treat polyatomic ions as a unit if they appear on both sides, and you'll have a quicker, easier answer for these more complex problems. Good luck.